We have finally reached what I would consider the interesting and fun part of the course, which is well into chapter 3, but we're here. What we're really going to start doing now is talking about how ATP is created and consumed by our cells. We'll talk less about the consumption component because that's kind of highly specific to individual cells, but we'll talk about it some. And the main thing that we'll focus on is how cells make ATP. So the first thing that we need to talk about is why ATP, or let's say how ATP releases energy. Hopefully we know why it releases energy because it's an exergonic reaction where ATP, the reactant, has more energy than the products, ADP, an inorganic phosphate. But what about the specific reaction actually translates into the release of energy into the cell? So here's a molecule of ATP, adenosine and 3 phosphates, right? Adenosine triphosphate is ATP. We know that this is an energy transferring nucleotide. Okay, so when ATP is broken down, what happens is the 3rd phosphate is split off from the 2nd phosphate, so right here. These phosphates are attached to each other through what are known as high energy bonds. Some biochemists absolutely despise that term, but it's very commonly used, so we're going to say it. Certainly in a course like this, I think it's a reasonable expression. So if you break one of these high energy bonds between, let's say, phosphate 3 and phosphate 2, a lot of energy gets released into the cell. Right? You're splitting this high energy bond, and meaning that there's a lot of energy stored within that bond between the 2nd and 3rd phosphate. And if you break that bond, a lot of that energy actually gets released into the cell so that the cell can perform different types of mechanical or chemical work. Now, what are you left with? We already know this because we've talked about it. You're left with ADP now. Adenosine diphosphate. You're left with adenosine, and then you're left with 2 phosphates. And what also do you have? You have this inorganic phosphate. And additionally, this will be less important for this course, but it's not a bad thing to know. The 3rd product that you have is actually a hydrogen ion. Those are the 3 products of what's called ATP hydrolysis. When you break down ATP, you do it through a hydrolysis reaction. Actually use water to accomplish this. Remember, in hydrolysis reactions, water is actually brought into the chemical equation or the chemical reaction in order to split something apart. And that's exactly what happens with the breakdown of ATP. It's a hydrolysis reaction. And there's also an enzyme involved, but we're not talking about that right now. So what you end up with in terms of the products are ADP, inorganic phosphate, and a hydrogen ion. Now, sometimes in certain textbooks and in certain courses, you might hear that energy is a product as well, because energy is released in this equation. I wouldn't try to argue that that's inaccurate, but that is not something that I would ask about on an exam. If I'm talking about the products of ATP hydrolysis, the breakdown of ATP, it's ADP, inorganic phosphate, and a hydrogen ion. I'm not talking about energy. I wouldn't include energy as a product. That's just my personal feeling about the matter. So cells are constantly consuming ATP in this way in order to have the energy that's necessary to perform their chemical as well as mechanical processes. The amount of ATP that will be consumed by one cell to the next is vastly different. Neurons and skeletal muscle cells consume enormous quantities of ATP. Epithelial cells, which are almost dormant for the most part, consume hardly any ATP. Why do I say that? Because it's going to become relevant very shortly in this conversation. The next thing that cells are constantly then having to do is resynthesize ATP, right? If a cell is consuming ATP, then it needs to resynthesize that ATP so it has more of it. If a cell runs out of ATP, we know that the cell will die because, as you'll see, you actually need ATP to make ATP. So cells can't run out of ATP. Most scientists agree about this. So they're constantly having to resynthesize it. And that's a big part of what we're going to look at in this whole chapter is how do cells resynthesize ATP? There's many different ways. Let's not say many different ways, but there's many different means by which they can accomplish it using similar pathways. So here you're seeing this. You've seen this before, right? You have ADP, you have inorganic phosphate, and you need to recombine them in order to form ATP. First of all, these are terms that you've seen before. This is a phosphorylation reaction. The last one was obviously a dephosphorylation, right? Because ATP lost a phosphate, and now in this reaction, ADP is actually gaining a phosphate, so it's been phosphorylated. When you resynthesize ATP, it is being phosphorylated. When you break down ATP, it's being dephosphorylated. Okay. Also, what do you have here? This is also a condensation reaction because what's going to become extracted in the reaction is water. That's the opposite of when you break down ATP. Right? When you break down ATP, you're splitting it apart, and in order to do so, you have to bring water in, so it's called a hydrolysis reaction. This time, when we are trying to synthesize ATP, we're bringing ADP and inorganic phosphate back together, and we're actually going to extract water in order to bring two things together, which is what you see in these condensation reactions. And then lastly, this isn't always going to be an endergonic reaction. You're going to have to bring energy into this chemical reaction, this chemical equation, in order to recombine ADP and inorganic phosphate, which is also the opposite of ATP hydrolysis, the breakdown of ATP, right? That's a huge exergonic reaction. In this reaction, we know that ADP and inorganic phosphate, which now serve as the reactants, actually have less energy than ATP, which is the product. So if you want to make ATP out of ADP and inorganic phosphate, which actually have less energy within them, you're going to have to put energy into the equation. So everything about the resynthesis of ATP, recreating ATP from ADP and inorganic phosphate, is the opposite of the breakdown or hydrolysis of ATP. I mean, it's logical, it makes sense, but these are putting a lot of terms together that we've been using throughout the last couple weeks. So now we're going to pivot to actually talking about systems that cells use to resynthesize ATP. And that will require a little bit of a conversation about cells consuming ATP. Most cells in the human body have these pathways, but I'm going to talk about muscle cells because skeletal muscle cells, the type of muscle that we use when we exercise. This is something I know a lot about. By consequence of me spending, decades studying it. So it's something very easy for me to create application with, which in my opinion is always what makes learning about this kind of stuff fun. But please know, generally you can apply these systems to most cells in the human body. I'm just going to focus on skeletal muscle cells because, like I said, it's easy for me, and I like to take the easy way out as it relates to this. So this first system that all of our cells have, but especially our muscle cells, is what's referred to as the phosphagen system. Another term that's oftentimes used for it is the ATP-PC system. That stands for adenosine triphosphate and phosphocreatine. You can see them both actually right here. This obviously is ATP, and over here you have what's known as phosphocreatine. And if any of you have ever heard of creatine supplements, that's going to fit right into this whole conversation. And it's actually, like I said, applicable to all of our cells, not just muscle cells. So within every muscle cell, there's going to be this phosphagen system. And what the phosphagen system is made up of, like I said, is ATP and phosphocreatine. And I think you fairly easily could actually make the argument that the phosphagen system is really just phosphocreatine, but it's hard to have the conversation about the phosphagen system without mentioning ATP. Okay, so in every single muscle cell, what you'll hear is that there's a certain amount of stored ATP. I don't really like that term, but it's technically true. There's a certain amount of ATP that already exists inside of the muscle cell. And in reality, the muscle cell is actively making it, so it's just there. There's a certain amount of ATP that always exists inside of all the cells in our body, and especially in higher quantities within our muscle cells. This varies depending upon how far you are from, let's say, the mitochondria to the plasma membrane, but generally speaking, there's about 1,000 ATP molecules for every one ADP molecule. The ratio is about 1,000 to 1. Again, it's very different depending upon what part of the cell you're looking at, but the amount of ATP within a cell is always substantially higher than the amount of ADP within the cell. So that is technically what people call stored ATP within the muscle cell. And additionally, there is some of this what's called phosphocreatine, and that really is the important part of the phosphagen system. So when is this system going to be used by our cells, particularly our muscle cells? When would it be used? Why would it be used? How does it work? First of all, within all the skeletal muscle cells of our body, there are these actin and myosin proteins. We'll talk about them in much, much more detail later on in the semester. But when muscle cells contract, what actually happens is these little myosin heads, as they're called, they're part of these myosin proteins, they actually swivel. They swivel and they attach to these filaments called actin, these proteins called actin. We'll talk about all this, like I said, later on. Not something you need to know for the exam right now. I'm just trying to provide a little bit of context. So when muscle cells contract, those little myosin heads, they sort of swivel and interact with these actin filaments. And in order to do that, they actually have to consume ATP. So the point is, as we're about to talk about, if a muscle cell goes from not contracting much to all of a sudden contracting a lot, in order for that muscle cell to contract a lot, it's going to have to consume more ATP, because a muscle cell contraction equates to the interactions between these myosin proteins and these actin proteins. And what enables them to interact and thus contract is ATP. So the more of a contraction that you have, the more that ATP is going to get consumed. You don't, like I said, I think people sometimes worry about this every semester. I'm not asking you about the anatomy of skeletal muscle cells right now. I'm just showing you, kind of how and why more ATP would be consumed by muscle cells if you ask them to contract more. We'll get to all that later on, how it actually all occurs. So what I would like you to do is think about what's depicted in this image, which is somebody starting a sprint. When we sprint, generally what do? We try to go from 0 to 60, and by 0 to 60, I mean from nothing to as fast as we can possibly go, in no time, right? We try to do it as absolutely fast as possible. We're in blocks, then the beep goes off, or whatever is used to signal the start of the race, and then you start running out of nowhere as fast as you possibly can. What I'd like you to do is think about, what do you think is going to happen to the ATP demand within her muscle cells? Right? Her ATP demand while she was in the blocks was, basal levels, like not all that much. It was typical resting ATP consumption. Right? It's not that her muscle cells weren't consuming no ATP, but they weren't consuming that much. And now, all of a sudden, she starts sprinting. What's going to happen to the rate at which those muscle cells start consuming ATP? Right? She's going to start contracting her muscles as frequently and as forcefully as she possibly can in this race. And what does that mean for the amount of ATP that her muscle cells are going to begin to consume? It is going to rise dramatically to the highest possible levels, or at least very close to them. her muscle cells are going to go from really not contracting hardly at all in the blocks to all of a sudden contracting as forcefully and as frequently as humanly possible. Okay? So her ATP demand within those muscle cells is going to go through the roof. This is where the phosphagen system comes into play. If her muscle cells, again, here's some muscle cells within her hamstrings, if these muscle cells all of a sudden have an enormously high ATP demand, we'll add the word demand here, her ATP demand goes up dramatically. Okay, what does that mean? If we think of what we spoke about just a few minutes ago, if her muscle cells start consuming tons of ATP all of a sudden, then she also needs to start resynthesizing ATP very, very quickly, because her muscle cells are going to start consuming huge quantities of ATP, and she also then needs to meet that demand. It is fundamental to human life that our cells attempt to, and oftentimes accomplish, meeting whatever the ATP demand of the muscle cell is, or whatever cell you're talking about. What I can tell you is, when the ATP demand gets enormously high out of nowhere, it's very difficult for any system to meet this ATP demand. When ATP demands are very, very high and they come on out of nowhere, all of a sudden trying to meet that ATP demand is very, very hard for your muscle cells. Think about it. All of a sudden the muscle cells, go from consuming very little quantities of ATP to consuming enormous quantities of ATP once this sprint has started. So what I can tell you is, in order to meet this ATP demand, the systems that are usually used to make ATP are not going to work, right? It takes those systems a while to turn on, as you're going to see later on in the semester, and beyond that, they're just simply incapable, at the end of the day, of actually meeting this high of an ATP demand. So what's going to actually happen at the beginning of this sprint is the ATP demand from the muscle cells is going to be way higher than the supply. The demand of ATP from her muscle cells, the muscle cells that are contracting within the sprint, I'm talking about hamstring, calf, gluteal muscles, quadricep muscle cells, their ATP demands are going to be substantially higher than what they can actually supply in ATP. We haven't talked about the other systems yet, but I'll say it again. Those systems take a while to turn on, and in reality, they wouldn't be able to meet this high of an ATP demand anyways. For those of you that have had biochemistry, what I'm talking about is beta oxidation and glycolysis. So now we have to ask ourselves, well, what's going to happen then? The initial answer is quite simple. If the ATP demand is higher than the supply, what's going to accumulate? If more ATP is being consumed within the cell than is being made, what will accumulate? And the answer is ADP and inorganic phosphate and hydrogen ions. But ADP is going to accumulate because the muscle cells, again, the muscle cells within her hamstring muscles that are contracting, quadriceps, so forth and so on, those muscle cells within those muscles have a much higher demand for ATP than is being supplied. So obviously what will start to accumulate in the cells is the products of ATP hydrolysis, which is ADP, inorganic phosphate, and so on. So what does that mean? Well, what ADP will do is it will come over and it will start binding to a regulatory site on this enzyme called creatine kinase, sometimes called creatine phosphokinase. And this is what's called, as you've seen before, allosteric activation. ADP actually binds to this enzyme's regulatory site and increases its affinity for its reactants. So the first thing to see here is ADP, when it starts to accumulate inside of muscle cells, it'll begin to allosterically activate this very important enzyme, creatine kinase. And now the next question is, what is creatine kinase going to start to do? Creatine kinase, what it does as an enzyme is its reactants are two things, phosphocreatine and ADP. So the reactants for creatine kinase are phosphocreatine and ADP. First of all, what's phosphocreatine? It's two things. It has a creatine group and a phosphate group. And the creatine and phosphate group are attached to each other through, I'll draw this in red, a high energy bond. Well, that's convenient. So inside of the muscle cells, this is the other component and the main component of the phosphagen system, is phosphocreatine, which is phosphate bound to a creatine molecule through a high energy bond. So what creatine kinase will do is it'll bind to phosphocreatine and ADP, and it will initiate this chemical reaction. And in this chemical reaction, here's what happens. The phosphate is broken off of creatine. That high energy bond is broken. And what ultimately happens is the phosphate and the energy from that bond is transferred to ADP. And what do you think gets reformed or resynthesized? ATP. If you can remove the phosphate off of creatine and give that phosphate to ADP, what do you make? Well, you add a third phosphate to adenosine diphosphate to make adenosine triphosphate. You've just resynthesized ATP here. That's one of the products of this reaction. And what is the other product? Well, all you've got left is creatine, because you stripped the phosphate off of phosphocreatine, so now all that's left is creatine. So the two products of this reaction are creatine and, most importantly, ATP. You've resynthesized ATP in this reaction. That's the important part. And you did it by taking the phosphate off of phosphocreatine and giving it to ADP. What you're actually seeing at work here is now what is called the phosphagen system. As I've tried to make the point, phosphocreatine really is the most important part of the phosphagen system. You can't talk about the phosphagen system without talking about ATP too, but phosphocreatine is it. It's used to actually quickly donate its phosphate to resynthesize ATP from ADP. Or maybe I could say that more eloquently. It's used to donate its phosphate to ADP to resynthesize ATP. Now we have to talk about why this reaction is so important, and why would it be used in this circumstance of a sprint? And that requires you to go back and think about the circumstance. Within the muscle cell, all of a sudden you have this incredibly high ATP demand, right? This very high ATP demand came out of nowhere. And you have to meet this enormously high ATP demand that came from nowhere, came from nothing. And how are you going to do it? The regular systems that we would typically use to resynthesize ATP, it takes a while to turn those on, and they're honestly too slow anyways. So what makes this system, the phosphagen system, so good at meeting very high and immediate ATP demands? And the answer is, it can resynthesize ATP in one single reaction. There's no other system that can do this. And what do I mean by that? In one reaction, we resynthesize ATP. How? Think about it. You're going to see all these other systems take many, many reactions to actually make ATP, which means it takes those reactions a lot longer to actually make ATP, which is part of the reason they can't meet enormously high ATP demands anyways. This reaction does it all with, at once. All it does is it takes a molecule of phosphocreatine, breaks it down, donates the phosphate to ADP, and resynthesizes ATP. In one chemical reaction, we've remade ATP. That means this phosphagen system can resynthesize ATP at an incredibly rapid rate. And the reason it can do it is because it only takes one reaction to actually resynthesize ATP. There's no other system that can do this. So, under instances where the ATP demand is incredibly high and immediate, this system will benefit the muscle cells and other cells in your body as well in that circumstance. And the reason is because it can make enormous quantities of ATP over a very short period of time. The best way to say it is it can resynthesize ATP at an incredibly rapid rate because it only takes one reaction. So when ATP demands are enormously high and immediate, most cells will rely on this phosphagen system to some degree. So before I talk about the phosphagen system more, I want to talk about something else related to the phosphagen system that's relevant to all the things that we've been talking about so far during this semester. And that is, why wasn't creatine kinase active from the start? Right? Because think about it. How did we activate creatine kinase? We needed ADP to accumulate inside of the muscle cell, and then it allosterically activated creatine kinase, which really started the phosphagen system, breaking phosphocreatine down, donating a phosphate to resynthesize ATP. So why wasn't that enzyme, creatine kinase, right here, right? Why wasn't creatine kinase active from the start? And the answer is, well, ATP levels were plenty high inside of the cell. Like when she was just in the blocks there, the ATP levels were plentiful inside of her muscle cells. And what ATP was actually doing is it was binding to the same enzyme. It was binding to creatine kinase, and it was actually allosterically inhibiting it. Right? Because why would you need the phosphagen system running at a rapid rate when ATP levels are high inside of the muscle cell? What you're seeing here is actually feedback inhibition, right? If ATP levels are plentiful inside of the muscle cell, it doesn't need to be running the phosphagen system at a fast rate. So ATP, which is what the phosphagen system ultimately creates, if it's elevated inside of the muscle cell, there's no reason to run the phosphagen system, so it will allosterically inhibit the enzyme that is involved with it, and that will slow down the rate at which the phosphagen system runs. And then once you start the sprint, what begins to fall inside of the muscle cell? ATP levels begin to fall. And what begins to rise? ADP levels begin to rise. So what does the cell need to do now? ATP levels are falling and ADP levels are rising. Well, you better start a system that will start resynthesizing ATP, right? You need to get those ATP levels back up. And you need to do it quickly because this really, really high ATP demand came on out of nowhere. So what ADP will do is it will allosterically activate the enzyme creatine kinase to get the phosphagen system going to drive up those levels of ATP. I'm trying to tie together as many of these concepts as possible that we've been talking about to give them some context. This is actually very hard for me in the first couple chapters to talk about those things and then not provide you any real examples. And now you're actually seeing them. This was just a slide I was going to use with the last slide to talk about allosteric activation and inhibition of creatine kinase, but I ended up doing it without this slide. So the slide, I'm going to leave it here, but it doesn't actually serve any purpose. So now we're going to get back to discussing the phosphagen system as it relates to real life and try to give some examples of how we can apply this. So the phosphagen system, I think we've well established, is a system that can generate large quantities of ATP over a short period of time. It can make ATP really, really fast. The reason for that is because it can resynthesize ATP in one singular reaction with phosphocreatine. Now, what's the downside to the phosphagen system? Because there certainly is one, and that is cells in the body, especially muscle cells, don't actually store a lot of phosphocreatine. And phosphocreatine really is the phosphagen system because it's what's used to actually resynthesize the ATP. And if there's not very much of it, that would imply that this system can't actually last for very long. In fact, if you were to run the phosphagen system at its most rapid rate, a muscle cell, this varies a little bit from one person to the next, but a muscle cell would completely deplete itself of phosphocreatine and thus the phosphagen system within a matter of like 6 to 8 seconds. So it's a wonderful system at generating large quantities of ATP over a short period of time, but it also depletes itself very fast due to there not actually being much phosphocreatine in the muscle cells. All of it would eventually become creatine, because when phosphocreatine is expended, all the high energy phosphates are gone and all you've got left is creatine. What we're going to do next here is give a real world example of how we think we can show that the phosphagen system is in reality such a short-lived system because of this lack of phosphocreatine. This is a 100-meter dash, and it's looking at the 100-meter dash, 0 to 100 meters, and we have three very famous Olympic runners here. What you're observing is their velocity over the course of the race. So you can clearly see that their velocity substantially increases, which makes sense, as they run the race. But something very interesting happens. Look at this. First of all, the race starts. They come out of the blocks. We don't see 0 here, but we can assume that it's something like this, right? Their velocity goes up and up and up and up and up and up and up. And then what do you notice? There comes a point in time, and these are the best 100-meter dash runners of all time, by the way. They all completed the 100-meter dash within, 10 to sub 10 seconds. But what happens to every single one of them at the end? Look at that. Their velocity drops off. Every single one of these world-class 100-meter dash Olympic runners slows down at the end of a 100-meter dash. And you think, well, how could that be? Why would somebody be slowing down at the end of a 100-meter dash? And by the way, let me emphasize, nobody beats this rule. This is Usain Bolt, which holds the world record for the 100-meter dash. And if you look, Usain Bolt, at the end of the 100-meter dash, he slows down. His velocity drops off. It's true for everybody that has ever lived. Why? Well, first of all, they must be fatiguing at the end of the race. That is the logical explanation here. It's the only explanation that makes sense. There's some fatigue that begins to set in at the end of a 100-meter dash, and it happens to everybody. But when does the fatigue set in? And we can look at this and tell that in all of them, it happens somewhere around 80 meters. What is happening around 80 meters? Well, I would ask you, how far into the race are these athletes at 80 meters, time-wise? They're somewhere around 8 seconds into the race, around 80 meters. Well, how could that then relate to the phosphagen system? So, pick any one of these runners. The alarm goes off and the race starts. They go from 0 to 60 as fast as they can. By that I mean they try to run as fast as humanly possible. What happens inside of their contracting muscle fibers? The muscle fibers within their hamstring, quads, gluteal calf muscles. ATP demand goes through the roof. ATP demand isn't being met by supply, right? So what happens? ADP accumulates inside of their muscle fibers, allosterically activates creatine kinase, and creatine kinase begins activating what we could think of as the phosphagen system. That chemical reaction that breaks down phosphocreatine and which then can donate its phosphate to ADP to resynthesize ATP. So by activating this phosphagen system, right, this is what's happening during the race in all three of these sprinters within their muscle fibers. By activating the phosphagen system, what's actually happening is they're meeting their ATP demand. The phosphagen system can run fast enough so that ATP demand is being met by supply. The demand for ATP within their muscle fibers is being met by the supply of ATP. And what is strictly meeting that supply is this phosphagen system. The phosphagen system is so phenomenally good at resynthesizing lots of ATP in a short period of time that the demand for ATP within their muscle fibers is now being met by supply. It's a 1-to-1 ratio, which is exactly what they need. I tried to emphasize this. In every circumstance, cells want to meet their ATP demand with an ATP supply. And in this circumstance, we're going to need the phosphagen system within these muscle fibers to do it, because this ATP demand was so enormously high and came out of nowhere that you're going to have to rely on the phosphagen system to meet this ATP demand. And it can do it within basically all muscle fibers, we think, but for a very short period of time. Why? Because there's not much phosphocreatine within any given muscle fiber. When does the phosphocreatine run out? Somewhere around 6 to 8 seconds. So in these sprinters, all three of them, around 8 seconds into the race, phosphocreatine runs out. What does that mean if phosphocreatine runs out? So they're 8 seconds into the race, and there's no more phosphocreatine. All the phosphocreatine has actually been turned into creatine, so there's no more phosphocreatine. So what is that going to mean? Like, what's going to happen? And now we can go back to the image and say, well, what do we think is happening around 8 seconds? First of all, 8 seconds is going to happen right around somewhere around 80 meters. Okay, about 8 seconds into the race is when they'd be approximately at 80 meters. All right. We know that the phosphagen system is gone. The system that can resynthesize ATP the fastest, because it takes one reaction to do so, has been depleted because there's no more phosphocreatine. Now, what I would ask you is, do you think that their ATP demands have slowed down at, 80 meters, 8 seconds into the race? Absolutely not. Their ATP demand is still exactly the same. Their ATP demand hasn't changed at all. Right? They're still trying to run as fast as they possibly can. Right? So the demand of ATP within their muscle fibers hasn't shifted one bit. But what has? The supply. If within these muscle fibers this phosphagen system is completely depleted, it's gone, the system that can resynthesize ATP the fastest is vanished, right? Because the phosphocreatine is gone, which is what's actually used to resynthesize ATP. So their ATP demand is still significantly elevated, but their ability to run the phosphagen system and make ATP is gone, is depleted. Now, there's other systems, as you're going to see in the next chapter, that are also making ATP. But what I can promise you is if you remove the system that can resynthesize ATP the fastest, and you keep ATP demand the same, what does that mean for what's going to accumulate inside of their muscle fibers? Somewhere around 8 seconds, when ATP demand is substantially higher than supply, what will accumulate? Their muscle fibers are consuming way more ATP than their muscle fibers are making because of the depletion of this phosphagen system. So what accumulates? ADP, inorganic phosphate, and hydrogen ions. The products of ATP hydrolysis are just going to start accumulating exponentially within their muscle fibers, because their muscle fibers are going to be consuming way more ATP than they're making. The muscle fibers are going to be consuming way more ATP than the muscle fibers are resynthesizing. So the muscle fibers will continue to break down ATP at this really rapid rate without resynthesizing it, and then you're going to get an accumulation of all the products of ATP hydrolysis. And here's what we think that these products do. This is outside of the realm of this course by a mile in terms of how this happens and what are the theories related to it. But these ADP, inorganic phosphate in particular, and to some degree maybe hydrogen ions, they actually cause muscle fibers to fatigue. These are the molecules inside of our muscle fibers, if we allow them to accumulate, that actually cause our muscle fibers to fatigue, which would explain why fatigue sets in right around 80 meters or 8 seconds, and their velocity slows down. Because if the muscle fibers fatigue, they can't contract as forcefully and as frequently anymore, and that's going to cause them to slow down. We'll talk about why that would be necessary in just a second. But that's clearly what's going to happen here. At 80 meters, if the ATP demand is higher than the supply, due to the phosphagen system being depleted, the system that can resynthesize ATP the fastest, then ATP demand, again, stays completely elevated, exactly what it is, and the supply of ATP isn't being met, and all these byproducts that cause fatigue begin to accumulate. And that causes then these muscle fibers to fatigue, and the velocity drops off. This is why we think fatigue happens at the end of a sprint. It's because the muscle fibers are fatiguing for this particular reason. Now, people have long wanted to understand why fatigue happens. And I think it's become clearer and clearer why muscle fibers fatigue. Pretend that fatigue doesn't happen. The answer to what would happen would be pretty obvious. If fatigue didn't happen, right, what would continue to occur? First of all, maybe I should say it this way. As the muscle fiber fatigues after 80 meters or 8 seconds, if the muscle fiber fatigues and the fatigue causes the muscle fiber to contract less forcefully and less frequently, what's going to fall within the muscle fiber? ATP demand. Right? The purpose of fatigue, we think, is of course to reduce the demand of ATP from the muscle fiber so that it can be met by the supply. It's only logical. Right? I mean, you need, if the muscle fiber is consuming way more ATP than is being supplied to it, you need to now get the demand for ATP from the fiber down. And you can do that by fatiguing the fiber. Because if you fatigue the fiber, its demand for ATP will fall, and it can be met by the supply. And then you're back into this realm of what is basically homeostasis, where an ATP demand is being met by supply. The purpose of me saying that is to explain the real reason that fatigue has to happen. Pretend that fatigue doesn't set in. Right? If fatigue doesn't set in around 8 seconds or 80 meters, and you just allow the ATP demand to stay continuously higher than the supply, what will eventually be completely depleted inside of the muscle fiber? Clearly, ATP, right? ATP will be gone after a very short period of time. If you allow for that ATP demand, meaning the muscle fibers don't fatigue ever, they just, like, we wouldn't technically have to fatigue. Don't let the muscle fiber fatigue at all. And if that happens, the ATP demand within the muscle fiber will be forever higher than the supply of ATP after the phosphagen system's gone. And then what will the muscle fiber do? It'll completely deplete itself of ATP until all the ATP within the muscle fiber is gone. And then the muscle fiber would die. Because without ATP, as you're going to see, you can't make ATP. So you need ATP. And within the muscle fiber, in order for it to survive, muscle fibers and any cell in your body cannot completely deplete itself of ATP, or it will vanish, like it'll die. And I mean, vanish as in, go through necrosis. It'll die. There's a real reason, and by the way, skeletal muscle fibers, they can't really regenerate. So your muscle fibers have an incredibly strong drive not to die. And we think that fatiguing prevents death of the cell, right? Because if the muscle fiber fatigues around 8 meters or 8 seconds, then the ATP demand will fall closer to supply. And now the demand and the supply are the same. And then the muscle fiber won't completely deplete itself of ATP and it won't be at risk of death. Right? But if the fatigue didn't happen and the ATP demand was to stay elevated above supply, then of course, eventually the muscle fiber, and it wouldn't be eventually, it'd be very fast, the muscle fiber would completely deplete itself of all of its ATP, and then it wouldn't be able to survive anymore. So we think that fatigue within muscle cells and other cells throughout the body is a form of self-preservation, right? It prevents death of those cells. All right, so I think you've gotten a pretty good now introduction to metabolism. This phosphagen system is one of the many metabolic pathways that your cells use to make ATP. And I'll very quickly finish with this. This is not like an exercise physiology course, but I get this question every semester, especially when I teach in person. What about creatine supplements? People have been taking creatine supplements forever. If you go into any gas station, you go into a GNC, a vitamin shop, whatever, you'll find an abundance of creatine supplements. They even put creatine in Powerade now sometimes. I don't know if they're still doing that, but they were for a while. The purpose of taking creatine is you're actually consuming a bunch of this molecule. And you're consuming that molecule with the hopes that it will get into your skeletal muscle cells. And then once creatine is within your skeletal muscle cells, this happens while you're resting, right? Anybody that's ever taken a creatine supplement, you're supposed to take it 30 minutes before you work out, or you take it multiple times a day. You're taking it while you're at rest. And the idea is you take the creatine supplement, and the creatine gets into your muscle cells, and then inside of your muscle cells, what happens to creatine is it gets phosphorylated. A molecule of ATP actually comes along and donates a phosphate to creatine to make phosphocreatine. Right? But this is happening when you're resting, right? So you're not like consuming ATP. Like there's plenty of ATP inside of the muscle cell at rest, and this process can be run with no problem at all. ATP demands are enormously low when we're resting. That's why you take the creatine supplement before you work out. The idea is to build up a whole bunch of phosphocreatine within your muscle cells, more phosphocreatine within your muscle cells than there would normally be. The idea, of course, is pack your body with creatine through supplementation and then hope that the amount of phosphocreatine inside of your muscle cells is more than it would normally be. And how would that benefit somebody with performance? So here's this 100-meter dash, but now pretend that these 3 athletes have taken a creatine supplement before the sprint, 30 minutes to an hour before the sprint. And we're going to pretend that there's a whole bunch more, and that's not actually how this is going to end up working because we studied this, but let's pretend there's a whole bunch more phosphocreatine within their muscle cells than normal. Okay? What was going to happen then at 8 seconds or 80 meters if there's more phosphocreatine within their muscle cells than there normally is? Okay? If they've elevated the amount of phosphocreatine, the phosphagen system will last longer. Right? If there's more phosphocreatine within their muscle cells, the phosphagen system, of course, is going to last way longer than it would otherwise, than if they hadn't taken the creatine supplement. So if they have a phosphagen system that can last longer, what should happen around 8 seconds or 80 meters? Should they fatigue? That's the question that I normally ask, and the answer is no. Around 80 meters or 8 seconds, they shouldn't fatigue anymore because the phosphagen system can last longer. There's more phosphocreatine. So the system that can resynthesize ATP the fastest should last longer. And that very high ATP demand should be being met by supply for longer. So fatigue shouldn't set in around 80 meters or 8 seconds. The idea of a creatine supplement is to increase the amount of phosphocreatine within a muscle cell and delay fatigue, because you've increased the amount of time that the system that can resynthesize ATP the fastest can last, the phosphagen system. So what we would see is either their velocity would continue to elevate for a little while or it would plateau for a little while before a drop-off happened. And that would, of course, improve their 100-meter dash time. I mean, if you can delay when fatigue sets in and maintain a peak velocity or continue to increase the velocity, then of course you're going to finish the race faster. And that's the idea of creatine supplementation. And then of course I get the question, well, does it work? And people have been studying this scientifically for like a very, very long time, well over half a century. And the evidence is pretty clear that it does work, but it's very minimal. With 100-meter dash times, it might help somebody improve their 100-meter dash time by, a couple tenths of a second. There's plenty of research to suggest that that's true. That can make a big difference, for sure. If we relate this to like weightlifting, if so, you have to think of a type of lift that would last, 8 seconds or more. Let's relate this to like it depends upon the person and how fast they lift weights, but 4 to 5 rep max, that might take around that length of time. Maybe some people could get a couple more reps in. Taking a creatine supplement might allow someone to perform an extra repetition, more so than they would have without the creatine supplement. There's plenty of research to suggest that that works. But it only works for about the first 3 sets, and then the benefit is gone. And again, like I said, in a sprint, it may allow someone to improve their sprint by a couple tenths of a second, which again, some people would certainly argue that's a lot. Now, there's a lot of research also that suggests that creatine supplements do nothing. But I would say that there's more studies that suggest that they do something minor than nothing at all. But the advertisements, at least the way that they used to be in the 90s, where the suggestion was that, you take a creatine supplement and you'll pack on 20 to 30 pounds of muscle, it's outrageous. That's not what happens. It's not going to work that way. If you take something like an anabolic steroid, which is testosterone or a derivative of testosterone, then people easily can put on 20 to 30 pounds of muscle over the course of a month. With a creatine supplement, you'd be incredibly lucky to put on half a pound of muscle extra over the course of a month. It provides a minimal benefit to performance. And additionally, it tends to significantly increase water weight too, because it increases the osmolality of like muscle cells, and it tends to pull more water into the muscle cells. So people tend to gain a lot of weight when they take creatine, but it's all water. And then you think about that, like what if someone were to put on 15 pounds of water weight by taking a bunch of creatine supplements? What do you think would happen to their 100-meter dash time? If you weigh 15 pounds more, your 100-meter dash time could actually go down. So that's a whole nother conversation. There's so many things to talk about with creatine supplementation that are outside of the realm of this course. But every semester I get lots of questions about that. So I always feel obligated to to give you a little bit of information about these supplements and what they're trying to do. They're trying to basically increase the amount of phosphocreatine within muscle cells and cause the phosphagen system, the system that can resynthesize ATP the fastest, to last longer and thus delay fatigue, which can help performance. But please don't be oversold by what they do. Supplement companies would love you to believe that they're a miracle drug that can, I mean, it's not even a drug. There's tons of creatine in meat. You can eat an enormous amount of meat and get as much creatine as you would in a supplement. So to call it a drug is kind of silly. But again, these companies would love for you to believe that it'll change your life, and it won't. But it can make a minor difference. I'll leave it at that. If you have a real interest and passion about this, I'm always open to talking about it with you. That brings us to the end of the phosphagen system. This first system that we use, that our cells use, and we focused on muscle cells to resynthesize ATP. It is a system. It is a metabolic system, which is what this chapter is all about: metabolism.